In the last video, I explained you what you mean by plastic deformation and its types of mechanisms. And here I want you to remember, in plastic deformation, slip happens because of shear stress. Am I right? Yes. So in this video, I am going to explain you how to obtain the critical resolved shear stress to cause slip. In order to find the expression for critical resolved shear stress, I am going to consider a cylindrical crystal. Okay, so here what I am going to do is just I am applying tensile load. I am going to apply tensile load, just a pull on both ends. Is a tensile load I am going to capture as F is applied load. And what happens when the tensile load is applied? It tends to what? Slip, right? So here I am going to consider the slip going to happen at this particular region. This is the slip plane. So if it is a slip plane, the slip will happens. The slipping will happens in the direction like this. This will be the slip direction. I am going to take it as tau d, slip direction. And next, the slip perpendicular to this slip direction, there will be a force which is called as normal. This is called as normal. This is a normal force which is 90 degree or perpendicular with what? Slip direction. I can also take the observation, this slip direction and this slip normal making an angle with the applied load, right? So I can take this angle between this applied load and slip normal as pi 1, and I can also take the angle between this slip direction and the applied load as pi 2. Okay, so now here we have the area, am I right? Here we have the slip plane area. So this is the area of slip plane. So I am going to give this as AS, area of slip plane. Again, see here we can have the area of this cylindrical crystal, area of cylindrical crystal. So that I am going to take as A. Okay. Now we are going to find the expression for critical resolved shear stress. Okay, and in general we used to represent the shear stress as tau, and here we are going to represent as tau or SS. Okay, and generally we know shear stress in the sense load divided by area. Am I right? The same mathematical expression we are going to derive this critical resolved shear stress. Same, load divided by area. Okay, so I can write load as Ft, that means force acting in the direction of slip, divided by area of the slip, and the force acting in the direction of what? Slip. That's why I have written Ft, and here I have to capture area in the slip plane. Okay, fine. So now to generate the expression, we want to know the data for Fd and area at the slip line, right? So let's do that. So first we can begin with the force in the slip line. Force in slip line, that means Fd. So I can say force in the slip line is F into cos pi 2, right? So that means, so it is taken to find the force acting in the slip direction is equal to force, that means normal tensile force acting in the cylindrical crystal, okay, in the cylindrical crystal, into cosine of the angle between force and what? Force in the slip plane, this direction, angle between this force and tau t. Okay, so in general we know in order to resolve the force we used to multiply with the cosine and the angle, right? The same thing we have done here. Okay, fine. So now we got the ft value. So now we are going to find the answer for slip area. Slip area. So area of slip AS is equal to, I can say we have idea, that means with respect to the crystal area, I can say that crystal area divided by cos of angle between this force and the normal by 1. Okay, so S. So now one more thing we need while we are solving this thing to find the expression. So I can take now itself, we need force F. So I can say force F acting on the cylinder or crystal cylinder, that means force acting on area A for the cylinder crystal. Here I have mentioned A is equal to, that means F is equal to, I can say sigma into A. So this is derived actually from we have the mathematical expression for engineering stress, you know, that means stress is equal to force divided by area, force acting per unit area. So from this expression we have taken what, this tensile force value, right? So now we can try to substitute those things, that means FD, force acting the slip direction, as well area of the slip, in the main formula. Okay, so that means it becomes FD divided by AS is equal to try to substitute FD is here F cos pi 2 divided by, so here for area we have A divided by cos pi 2. So now just have a look at this expression. We have F divided by area, right? F divided by area. So you see here, so for stress sigma, we do know the expression sigma is equal to F divided by A, right? So try to substitute those things in this expression. That means it becomes sigma. That means F divided by A can be simplified into sigma, and we can write sigma cos pi 2 divided by 1 divided by, so 1 divided by cos pi 2, right? If again I simplify this expression, I can say this tau or SS, okay, critical resolved shear stress as sigma into cos pi 2 into cos pi sigma cos pi 1. So here I have committed a mistake. Actually for area of slip it is A divided by cos pi 1, right? So it must be 1. So this also pi 1. Okay, so this would be cos pi 1. So this expression came from the previous step, just by taking a reciprocal of this value we got sigma cos pi 2 into cos pi 1. Okay, this is the expression for the critical resolves shear stress. From this expression, one more thing I can say, that means the cause of slip is not only depends on the tensile test or tensile load or tensile stress applied on the crystal. It is evidently seen from this expression, that means it depends also on the slip plane. Okay, it's not only on the tensile stress applied on the crystal, but also it depends on the stress plane. So you can see here. Okay, so by this we can end up this session. Thank you so much.